So today we're talking about the concept of stress, and as you can see in this first little definition, a material is said to be in a state of stress when it resists the deformations produced by an applied force. Okay, then to quantify the amount of the stress, we talk about the intensity of stress and the magnitudes of the internal forces which resist deformation can be more conveniently compared when they are considered to act on unit area. Okay, and that's going to bring us to this formula that you see over here, where we have stress being equal to the applied force over the area that is resisting that force. Now, as can be seen from that little formula, the units are then going to be newtons upon meters squared, and that is better known as pascals. Right, now two ways we can look at the stress. Firstly, we're going to be talking about direct stress in two ways. The first being tensile. Now, if you look at this little drawing over here, we've got an applied force of P, which is tending to stretch the specimen, which, if it was round, as in the case of this example here, that area under tension you would find by using the formula for area of a circle, pi upon 4d squared. That would go in here as area. And if you then knew the force P and you divided it by the area resisting this tension, you would have sigma, which is your stress value or your intensity of stress. Remember, the units are newtons per square meter or pascals. Now, in exactly the same way, if we are tending to shorten the specimen, note the directions of the arrows here and here. The force P is tending to make this specimen shorter, better known as compression. And we would have exactly the same formula, except that the value is negative in essence. Okay, we'll simply refer to it as tensile stress and compressive stress. So now we get on to the second type of stress that we're going to be dealing with, and that is the one called shear stress. Now, there's a nice little sketch below which shows typical shearing action of a specimen, and you can see that we have the force P pushing the lower half of the specimen from left to right, and conversely the top part of the specimen being pushed from right to left. Now that would cause shear to happen on this shaded plane that we have over here, and amazingly we still have a formula that looks very much like the one for direct stress. The only difference is we try and show that it is shear stress by using this Greek letter tau. And once again, it's going to be the value of the magnitude of the shearing force divided by the area that is resisting that shear. Now, a nice way to understand shear stress and shear area more easily is to consider a pair of scissors cutting a piece of paper. So if I just make a little sketch here, if you look at a pair of scissors, effectively there are two blades that are passing close to each other, and the piece of paper, I'll draw in red, would fit between those two. And as the one blade of the pair of scissors goes down, that's this one over here, the other blade rises, and the piece of paper is not cut, the piece of paper is actually sheared. So that would be one way of seeing shear stress. If we move on to double shear, the area simply becomes twice as big. And here's the sketch, double shear. We would have P being the force moving, let's call it the middle specimen from left to right. And then for equilibrium, we'd have P over 2 here and P over 2 there. That is to obviously get equilibrium as far as horizontal forces go. But now the area that is in fact resisting the shearing action is twice what it was before. You'll see there is one circular area in this case and another circular area there. So your formula would just be modified to allow for this doubling up of areas. That is better known as double shear. A simple way of illustrating double shear once again would be to build a simple part of a mechanism or machine structure like the one I've shown here. What we have is two blue plates parallel to each other, and there's a hole right the way through there, and we have the red plate which is going to fit between the two blue plates. It also has a hole, and I've drawn this green pin which is going to slot in to secure the whole lot. So we go to the next slide. If we were to apply a force in tension in this case, P to the right, applied to the red plate, and for equilibrium once again there'd be P over 2 in each of the blue plates. The blue plates might be attached to the same part of the machine to the left. That's not important to us at this stage. What is important is during this operation of applying tension, we would have a shear plane over here and over here, and you can see that means it's actually double shear. So this green pin is resisting the shear at 2 places, in contrast to the single shear which we did earlier. So to summarize, so far we've looked at stress as direct stress, and we looked at tensile and compressive. We then looked at shear stress, which had a very similar looking formula, but the whole concept was different because here we were shearing the material. This one was single shear and here was double shear. We've been through that. But before we move off this concept completely, we need to look at this next aspect of strain, which is often badly understood by learners. So let's go through this carefully. Strain, the concept of strain, is one to do with change in length versus original length. So let's look at the definition. A load acting on a material will produce a change in dimension. That might be a very small amount of change, but nevertheless, if you, like in the previous examples, applied tensile force to a specimen, you might not see it, but it would change in length, probably very little. It could be a lot more depending on what material it is, but the point is there would be a change in dimension. So this change in dimension per unit dimension is called strain. Now the per unit dimension is important, and that's what makes strain a ratio, and it has no units. So here's the formula. Direct strain is simply the change in length, how much the specimen or the sample changed in length, divided by its original length. And if we look at the units, we would have meters over meters. So it's a unitless ratio, and we denote it normally by the Greek letter epsilon. And there's the formula. Strain is change in length in meters over original length in meters. It's probably easier to understand that last concept by means of a sketch. So let's look at the tension scenario. There's our specimen attached to some fixed structure at the top here, and we're applying the force P. So as said before, the specimen is going to extend. There's going to be a change in length. It might be very small, but nevertheless it does exist. So that amount is going to be lowercase e, and the original length we're going to call capital L. So the formula epsilon, as we said before, change in length, however much it was in meters at the top, and underneath change in length in the same units, meters, and you're going to have this unitless ratio known as strain. Exactly the same thing, but in compression, the specimen is going to get slightly shorter. So there's your change in length once again, and you compare it to the original length. And once again, the same number is going to crop up. Okay, now things get really interesting when we start talking about shear strain. Now remember, shear, you have two forces acting in opposite directions, tending to place your specimen in shear. Okay, so in our case, if we say the one side of the specimen is fixed, that's what's denoted by these little hatched lines, and let's say we apply force P from left to right, there it is there. This top surface of the specimen is going to be pushed from left to right. The lower surface of the specimen is fixed. So the deformation that's going to occur might be very, very small, as we said. It's going to be that this point of the block has now shifted to that point over there. So your change in dimension, as abstract as it may seem, is going to be this small dimension over here, which once again we use the lowercase letter e for that. And now what might seem strange is the original length is now going to be the distance between the two shear planes. So shear strain is going to be E over L, exactly the same formula as before, but the concept is handled differently when it is shear strain. So to summarize, direct strain, change in length over original length. Shear strain, also change in length over original length, but we've got to understand what the change of length is and what the original length is as well. Next, let's look at a very simple example to do with strain. So here we have an example wanting to know the strain induced in a 2-meter length of steel bar. The axial load produces an extension of 0.57 millimeters. So strain is, as we know, change in length over original length. And you'll note here that we're not using meters over meters, but it really doesn't matter because it is, after all, just a unitless ratio. So here we've elected to put it in as millimeters. Remember, it was 0.57 millimeters, the change in length. Now the 2000 would be the original length, because remember the specimen was 2 meters long. And you plug that into your calculator and you get epsilon equal to 2.85 times 10 to the minus 4. But remember that we want to try and avoid minus 4, minus 7. So use your ENG button on your calculator. Press it once and it will offer you this option of expressing the answer as 285 times 10 to the minus 6. If you don't like that, you can always press Shift ENG and it'll make it 0.25 times 10 to the minus 3. Doesn't matter, none of the answers are incorrect, but let's try and stick to the format where we have 3s, 6s and 9s if possible as the exponent. Now, to finish off this section of theory, we need to look at two vital concepts that you're going to need for your strength of material studies. The first is this value E, and the second is the value G, both capital letters. The first one, E, is also known as Young's modulus. So I've written that over here. Now, modulus of elasticity, or E, same thing as Young's modulus, is simply direct stress divided by direct strain. So let's think about what that is. Direct stress, if you're applying tension or compression to a specimen and you are producing stress in it, and separately you can work out the strain that occurred when you did all of that, and you put the one value over the other, you come up with this quantity Young's modulus, or modulus of elasticity. Now that might not seem important to you at this stage, but it's a very useful way of expressing the material's properties. So when you're designing something in the future and you need to select a material, often you'll be using this value of E to select that material. Okay, now in a very similar fashion, but not to do with direct tension or compression, if you are selecting a material based on its shear strength properties, you'll be working with a very similar quantity called modulus of rigidity, denoted with capital letter G, where it would also be the stress over the strain, but in this case it would be the shear stress over the shear strain. So that brings us to the end of this little section, and the next project will be to do the tutorial.